welcome to semester 2. We're going to be starting off looking at it's not 18, it's actually 17. Chapter 17 talks about sampling distributions. This is kind of the main idea. And it may sound very similar to things that we've already done. We've used the phrasing a distribution of a sample versus a sampling distribution at this point. There's a bit of difference. So I want to kind of go over what all that entails. You can see here the major topics here are going to be the sampling distribution concept. You've got sampling error, the central limit theorem, and this chapter, kind of unique in this entire semester, will incorporate categorical data, proportions. And so that's kind of a keyword here that's really going to take prominence in this chapter or in this semester. Is the word proportion is always going to refer to a categorical variable. The word means is going to always refer to a quantitative variable, okay? And so keep in mind that this chapter will incorporate both concepts. The subsequent chapters that come after this won't entail both. They're only going to kind of figure out one or the other, and they'll kind of go through the process. All right, let's go ahead and get started. So first question is, what is a sampling distribution? How is that different from, say, a samples distribution? It's a pretty significant difference, even though the titles sound the same. The distribution of a single sample is what you're used to hearing. It uses a single sample. Think about the average height of students at Buford. You could go out and collect data, and you would use all that information to create a histogram, to create the statistics like the average or the standard deviation, and that's all going to use a single sample each time. It uses individuals to compute statistics. In this case, you do get a lot more variation than, say, the sampling distribution because we're using individuals. In other words, if I have a particularly tall person or a particularly short person, then those, what we would consider outliers, are just there and they're not combined with any other thing. So those are always present. So you're going to get the absolute minimum and the absolute maximum of a single particular population. And these all will follow whatever shape that distribution has to offer. If that distribution is skewed to the smaller or to the taller, or if it's symmetric, then it will show that. If it's bimodal, which is a probable, if we're looking at height, you've got the male height versus the female height. So that's going to have a particularly open scenario when it comes to displaying shape. Now, let's contrast that with a sampling distribution. What's going to happen is you're going to take a single sample like this, and then instead of putting let's say you took a sample of 100, instead of putting all of those numbers on a chart, you're going to take every number in that particular sample and you're going to average that number together. And you're going to use that one average to represent the one sample. So if we took a sample of 100, I'm going to average it together, and that's going to, that if I were making, let's say, a dot plot, then that one sample of 100 gets put on as a single average or a single dot on my dot plot, versus over here, each individual person gets their own dot. Okay, now here we have to take that sample. If I had 100 people over here, that would mean if I wanted to create let's say I had a dot plot of 100 people, if I wanted to get 100 dots again, then I have to take a sample 100 times and average that. Now, you don't have to take the sample of 100. I could take the sample of 20 or 30 or 40, whatever that I need, but I would have to average that number together. And I would have to take multiple samples. So if I wanted 100 dots, I'd have to take 100 samples, and I would have to average those numbers 100 times, and that would give me that same number of dots. But notice that I would have had a much larger representation of the population than I would if I'd used a single sample. Here, you're looking at only a sample of 100. Here, if I had 100 dots, then that would be 100 times however many I had in each individual sample, because each dot represents the average. So here you're using a lot more people, a lot more sample, you're getting a lot more information. Now, once I compute averages, right, I'm using averages to compute the statistics versus the individuals to compute statistics. So if you think about this, if the outlier of the height is in one of my samples, but I average it together with all the other numbers in that sample, I'm actually not going to get the tallest number or the actual outlier to show up in my particular set of data. So when I go to find the average of all of my averages, that number, when I make that dot plot or whatever, it's not going to show the absolute maximum, absolute minimum, because those had been averaged together with other things. So when I do that, it causes less variation to happen. So I don't, so it mutes all of my extreme values. So I'm not so susceptible to the really unusual observations in a set of data, which is good because those things tend to throw off all of my statistics from that value, right? So it'll give me less variation. And when I mean less variation, I'm being specific to measures of spread like range, IQR, standard deviation. Since my maximum and minimum values aren't as varied as much as it would be here, I'm going to have a smaller standard deviation, a smaller IQR, smaller range. Things won't vary as much because we're using average results. It tends to mute those extreme values, right? And here's probably the most important aspect of this. If we take a sample that is large enough, and there is a specific test for this, if my sample is large enough, then I can assume that that distribution will be approximately normal. Over here, I don't get that scenario. And this is why this is really important. If I use sampling distributions to describe something, it means that if my sample is large enough, then I get all the privileges and benefits and the distribution of the normal model. It means I know a lot about it. We can use normal CDF. We can use a lot of other things to talk about this, which allows us to talk about probability and how likely things are to happen at that particular value or higher or lower. And that's kind of the point of using sampling distributions, is that if I can make that normal distribution happen, we get all the benefits of that normal model. Right, and going back into specifics about shape, center, and spread, when I describe the distributions, just like last time, we talk about shape, we talk about center, we talk about spread, and we talk about those unusual observations. Even though I'm using averages, I can still get outliers to happen in a sampling distributions. They're just not as prevalent, or they're not as extreme as it would be if I had used the individuals. So with shape, the shape of the distribution will always be approximately normal if I have a large enough sample. Now, if the sample is not large enough to be considered normal, then that sampling distribution will tend to model whatever that population shape would be. So, for example, if we were talking about, let's say, the average height, then I'm probably going to end up with a bimodal distribution. However, if I use a sampling distribution to talk about it, the larger my sample gets as I'm taking the sample sizes, like let's say if I took samples of 20 and averaged them together to get that, or sample sizes of 50 or whatever, then the larger my sample gets, the more normal my distribution is going to be, right? But the smaller it is, the more like the population distribution shape it's going to mimic. So if it's skewed right to start off with, if I took just a single sample, then my smaller sampling distributions will be skewed right. But the larger I take, if I took samples of 10 and averaged them, or 20 or 30, the larger that number gets, the more approximately normal it would become. The center, now this is the really easy part about this chapter, is the center of your sampling distribution will be the exact center as the sample. So let's say the average height is, let's say it's 70 inches. Then the average of my population is 70, the average of my sampling distribution, no matter how big my samples are, whether they're samples of 10 or 20 or 100, the average will remain the same every single time. Spread. Spread makes a consistent situation. As we increase our sample size, we're going to be decreasing the spread, right? We kind of already talked about that. As sample size gets larger, spread gets smaller. And you can see that in the formulas as well. Okay. Sampling distributions have specific distribution assumptions and conditions. Okay. You'll find that in this chapter and the chapters that follow this in this semester, these things are going to become very important, and you're going to need to be really, really careful about checking each of these things. The good news about what you see here is that independence, randomization, 10%, success or failure, independence, randomization, 10%, large enough. Notice that lots of these things are the same, right? The one that's different is here because this references categorical concepts, successes and failures. Large enough indicates a specific sample can be approximately normal. Now, they're both addressing whether it can be approximately normal or not. Okay. If my n times p and n times q are at least 10, both of them, 10 or more, then we can say that the normal is approximately normal. And that word approximately normal is really important here. I use the word normal here. Probably should have said approximately normal. And so for the large enough here, in order for that, we don't have successes and failures, but we do have sample sizes that we take to average together. So what we want to do is assume it's unimodal and symmetric, which means approximately normal. We can make sure that the n, if n is larger than 40, we get to assume that it works out okay. Now, if the original population is unimodal symmetric, then small samples would be okay. But for sample sizes that are not original, in other words, if we pull from original population and say, hey, the original population is normal, then we can assume that my sample is going to be normal. I just get to make that assumption no matter how big of a sample it is. But if it's not normal, then we want to see my n size at least 40. Sometimes some books will say 30. I think we kind of just go with 40. And so whenever that happens, if you want to make sure that you have a normal distribution, then if your n is larger than 40, then we can assume that it's normal, approximately normal either way. Now, assumption, independence, randomization, 10%. These are the same ones that we're used to. We introduced these back last semester. So they're not going to really change a whole lot. I'll just kind of refresh your memory. Independence refers to each individual number that you collect is independent of the other. In other words, height, from one person's height to the next person's height, those things are independent. My height doesn't affect someone else's height. Randomization is about did I collect my data in a random fashion? Be careful if it's coming from an experiment, which you'll see show up from time to time. The volunteers must be randomly assigned to their treatments, right? Otherwise, it would be a survey. It needs to be SRS or needs to be unbiased. That's kind of the whole point. Randomization is trying to prevent any sort of bias in the way that you collect the data. 10%. If we go back to independence, these two are connected. If we know that it's truly independent, if I'm sampling without replacement, then we know that truly I'm not really getting independence, but we can kind of we get permission to use the sample even then, but I have to stay underneath 10% of the population. And the way that we check that is you take the sample size you have. Let's say our sample was 100. Then I would multiply that number by 10. So 10 times 100 would give me 1,000. I need to make sure that my population of interest is at least 1,000 or bigger, right? So if I'm choosing a sample of 100 from a certain city, then as long as my city has at least 1,000 people in it, then I'm okay with that particular sample size. Let's say Buford has 2,000 students, then I would be able to take a sample of up to 200 or less. If I took a sample more than 200, then I would be going over that 10%. And that would be, it would break that down. And since we're sampling without replacement here, I really couldn't consider this independent. And so that's kind of, these two things are connected together. And they're both true for both quantitative and categorical situations. They're both the same. It's the fourth one that is different for each one: large enough and success and failure. So we had kind of talked about this one before. This is a little bit, I guess this is pretty new. It's the same idea. We want to make sure that my sample is large enough for it to be considered approximately normal. And the way we do that is two different ways set up here. Okay. The last particular set of notes we're going to go through today is the specific formulas for mean and standard deviation in this chapter. Now the mean, notice here, the mean, we always represent the population mean as mu, the Greek letter mu. Now p hat and p are representing a proportion. And you're going to see usually when we give something a particular character above it, like x bar, p hat, these are representing the statistics, right? X bar here, when it's obviously that means average, and the population mean is equal to the sample mean. Here, same thing, but this is called a proportion. So the proportion of people, that's a percentage usually, of whatever would be here. So let's say you're talking about your favorite movie genre. If the percentage of people who their favorite movie genre is drama, then whatever percentage is in the population would be also the same percentage from the sample itself. Standard deviation formulas get a little bit more complicated, but they're not difficult. These are all located on your formula sheet. Note here that there's no formula. Like, it's just whatever I tell you that population mean is, that's also your sample mean, right? It will be listed in the problem. There's no calculation needed. It's given to you. Here, the standard deviation of the proportion for p hat is equal to the square root of pq divided by n. Now, symbol here, standard deviation, this is usually a quantitative denote. Here we use SD because it is categorical. So there is a bit of a difference here. You'll see this written, it can be both. Sigma, it just represents the population duration. I could have written sigma over here. Typically we don't, but it could be always denote this part here. That's going to tell you whether it's categorical or quantitative. So once you determine that, you're really not going to get worried about that too much. What you really are focused on is the particular formula. Here you have a P and a Q. Here you have a sigma and a sample size. So the standard deviation, if it is given to you, it will be a quantitative scenario. Over here, what's traditionally given is a P and an N. Here we have a standard deviation and an N. So P represents the probability of success, whatever that happens to be. And so these things, obviously you can see as the denominator, it's got an N in it. So as this denominator gets larger, the entire value of the fraction gets smaller. So as sample size increases, these two numbers here are going to get smaller and smaller and smaller. Okay, so here again, not a big deal to memorize these things, but they are part of your formula sheet. You will use them back and forth, and it will be something that's important to make sure I know how to calculate. So the big deal is note what's needed for each one and know how to distinguish between categorical and quantitative data. If you understand that, getting those two things are going to be pretty straightforward and simple. Now, some things that are going to happen is I could have a normal scenario, normal distribution, totally going to happen in this chapter. And remember, to do that, we set it up as the center and spread. The center and spread, right? So the mean and a standard deviation, when you type it in a normal CDF, you're going to be requiring these two bits of information. And this is the part that everybody gets wrong. This one, everybody usually gets it right because I'm not going to give you a standard deviation and you'll recalculate it as you need it. But this one, you're going to be given a standard deviation in the problem and you're going to be tempted to use that number in normal CDF without recalculating it for the sample size. but you've got to remember to do this. This is probably the single biggest mistake that people are going to make in this chapter. You're going to get all the normal probabilities wrong for quantitative data because you fail to change the standard deviation according to how big your samples are. So that is a pretty big deal. Make sure you know how to do that. If you don't, it's going to be a lot of points taken off because you failed to change that standard deviation.